Friends, in our previous video on chapter 3 of electrostatic, electric potential and potential energy, we learned the concept behind electric potential and potential energy, and we also learned the definition of electric potential and potential energy. If any one of you haven't yet watched that video, please click on the top right hand corner I button to get the link of the very same. Just to give you a quick revision, how have we defined electric potential energy? Electric potential energy was defined as the work done in bringing any point charge q naught with infinitesimally small speed, and this speed was needed to be held constant from infinity to some point in the electric field of any charge distribution. So the amount of work done in bringing any charge with infinitesimally slow constant speed from infinity to any point defines the electrostatic potential energy, friends. SI unit of electrostatic potential energy will be equal to the SI unit of work done, so that comes out to be in joule. Now, work done per unit charge in bringing a charge from infinity to some point P in the electric field with infinitesimally slow constant speed defines the electric potential, friends, and its unit was volt. So this definition we have already studied in our previous lecture session, friends. Friends, we are now going to obtain an expression for electrostatic potential energy and electric potential due to a point charge. So here, friends, what we are having a positive source charge of magnitude q, as you can see in a space, and it is fixed in a space. That means this charge is not free to move. That's I have taken just for the simplicity factor, friends. So how have we defined electrostatic potential or potential energy? Both were defined in terms of amount of work done. Amount of work done by whom? By some amount of work done by some external force, and this external force must bring a point test charge or point charge q naught from infinity to some point P in electric field. And how this be brought? This charge must be brought. This charge must be brought with infinitesimally slow constant speed, friends. So let's take my infinity to be farther away from this charge, and let me put it over here. So this is my infinity point, friends. Can you see over here? This is my infinity, and I am bringing some charge q naught that I am calling that as test charge. So I am bringing some charge q naught from infinity towards this source charge at some point P. So this is, I am bringing some test charge q naught, and presently this test charge is located at point x. So you can see this is the point where our test charge is presently located at some point x, which happens to be at certain distance x presently, and then I am going to bring this test charge to this point P, which happens to be located at a distance r from my source charge, friends. So this is what is the setup. I am bringing a test charge q naught from infinity to some point P with how I am bringing, that's with an infinitesimally slow constant speed, friend. So that's what the concept is. Now, when my test charge is placed at position x, it is already experiencing a repulsive force due to this source charge, and this repulsive force is Fe, and you all know this, the value of this Fe will be eventually be 1 upon 4 pi epsilon naught q1 q2, and here q1 happens to be the magnitude of source charge, that is q, and q2 happens to be the magnitude of test charge, that is q naught, upon whatsoever the distance. Presently the distance is x, upon x square. So I am just writing down it on the top, or over here, let's say Fe happens to be 1 upon 4 pi epsilon naught q1, that is q, q2, that is q naught, upon what is the distance between them, and that happens to be x square, friend. So this is the electrostatic repulsive force that my test charge experiences when it is placed at point x. Now, since I want to move this test charge towards the point P, so I have to apply some external force. The force that I am going to apply in order to overcome this repulsive force, I am going to call it as a FAG, and under the action of this FAG, my test charge will move a very small distance. Let's call it as dx distance, friends. So whatsoever the work I am going to obtain in this entire process in moving the charge from infinity to this point will give me the work done, and thereby it will help me to define the potential energy and potential of a point charge, friends. Now it is important for us to understand that FAG has to be just equal to FE. It should not be greater, it should not be smaller. Why? We have already discussed in our previous discussion, friends. So FAG has to be just equal to FE and directed opposite to it. I would like you all to think a little bit more why it has to be equal, so that you can refresh that what we have discussed in our previous session. Those who are not aware, please once again go back, look into that definition or concept, how we have defined electric potential and potential energy, friends. Now in order to define the electric potential and electrostatic potential energy, I need to find out the work done. So work done was defined as FAG into dx in bringing the charge from infinity to point R in the electric field, friends. So from infinity to some point P in the electric field situated at a distance R. Now we have already discussed why this force needs to be equal to minus times of Fe. The force that the agent applies has to be minus times of Fe. So you must have thought about it. I am leaving that as an exercise for you to once again keep pondering onto it. Now what is Fe? Now as I told you earlier also, Fe was the Coulombian force of repulsion. So Fe was equal to 1 upon 4 pi epsilon naught Q1. What is Q1? That is capital Q. What is Q2? That is Q naught upon whatsoever the distance where they are placed at a distance of x square x. So this distance happens to be x square. This is Fe. So what will be FAG? Now FAG will eventually be equal to minus of this, so minus 1 upon 4 pi epsilon naught Q naught upon x square. So this is FAG. Now this FAG has to be directed opposite, so that's why we are seeing the minus sign over here. The magnitude must be opposite. Now substituting the same into this expression, the work done by the agent will eventually be minus 1 upon 4 pi epsilon naught Q naught upon x square into dx. Taking the constant out, minus Q naught 4 upon 4 pi epsilon naught 1 upon x square into dx, or can also be written as work done is equals to minus Q naught upon 4 pi epsilon naught infinity to r x to the power of minus 2 into dx. On integrating the same, I would like you all to just pause the video over here and try to integrate this particular expression, friends. This one, you can all of you can do that. So pause the video over here, try it out on your own, and in the little bit you will get the result also. So the work done by the agent will be, you have done it, I am just doing it for you also, minus Q naught, the constants outside the integration 4 pi epsilon naught x to the power of n dx का integration क्या होता था, friends? It was x to the power of n plus 1 upon n plus 1. So x to the power of minus 2 है into dx, तो इसका इंटीग्रेशन क्या हो जाएगा? इसका इंटीग्रेशन आ जाएगा माइनस Q नॉट अपॉन 4 पाई एप्सिलॉन नॉट, और यहाँ पे इंटीग्रेशन हुआ x to the power of minus 2 plus 1 upon minus 2 plus 1. Our limits of integrations are from infinity to some point R. Let's solve it out once again. So this becomes minus Q naught upon 4 pi epsilon naught. X to the power of minus 2 will be x to the power of minus 2 plus 1 will be x to the power of minus 1 upon minus 2 plus 1 only minus 1, and limits of integration are infinity to R. And this minus 1 moves out of the bracket and combines with this minus to give me plus expression. So it becomes plus Q naught 4 pi epsilon naught, and the limits now, x to the power of minus 1 can be written as 1 by x, and the limits of integration is from infinity to some point r. Applying the limits, friends. So on applying the limits, friends, work done by the agent, this I am bringing it over here, friend, from here, please just pay attention. So work done by the agent will be q naught upon 4 pi epsilon naught, limits 1 upon upper limit, that is 1 by r, minus 1 upon lower limit, that is infinity. Now what is 1 upon infinity? It is 0. So this expression then becomes q naught upon 4 pi epsilon naught into 1 by r. Now this is the work done by the agent in bringing the charge from infinity to some point P in the electric field. So this happens to be my expression, 1 upon 4 pi epsilon naught q naught by r. So let me just do that. Let me just rewrite this expression as 1 upon 4 pi epsilon naught q naught upon r. And remember, friends, how have we defined electrostatic potential energy? Electrostatic potential energy was defined as the work done by bringing a charge from infinity to some point P in the electric field with infinitesimally slow constant speed. So all those things I have taken into account. So this expression is going to define me the potential energy of the system. So what's the expression for potential energy, friends? The expression for potential energy now happens to be 1 upon 4 pi epsilon naught q naught upon. So this becomes the expression for potential energy. So potential energy, remember, friends, is between a pair of charges. So you can see there were two pairs of charges, 1 upon 4 pi epsilon naught q and q naught. These were the two pair of charges. So potential energy is between these two pair of charges, and it equals to be 1 upon 4 pi epsilon naught q naught upon r. So r happens to be the distance of separation between the two charges. Here you should understand that potential energy depends upon two factors. One, both the pairs, magnitude of the charges of both the pairs, so this magnitude of the charges, and secondly it depends upon the distance of separation. It does not depend upon how I have brought the charge. See, from I, if I am bringing the charge like this to this point also, even then the potential energy will remain the same. And if I brought it like this, even then the potential energy would be same. From here, if I am bringing it like this, or if I am bringing the potential energy directly from here, bringing the charge directly from here, the manner in which you are bringing the charge, potential energy is independent of the manner, the path that you have taken. It only depends upon the initial position and the final position. So that's what is very important for you all to understand, friend. Also, as you know, we have defined the potential being equal to work done by the agent bringing the charge from infinity to some point r divided by the magnitude of the charge that you are bringing. So this is and this work done has already defined the potential energy over here. So the expression can also be written as potential energy upon q naught. So divide this expression by q naught, you will be getting the value for electric potential, and that comes out to be 1 upon 4 pi epsilon naught q by r. So here, friends, now you have got an expression for electric potential. So both these expression defines the electrostatic potential energy between, this defines the electrostatic potential energy, between pair of charges. And remember, potential energy is always for pair of charges, and this expression defines the electric potential due to a point source charge. So if you remember, our source charge was Q. So you can see in this particular expression we have got Q, and this Q happens to be the magnitude of source charge. So electric potential at this particular point depends upon the magnitude of the source charge, friends, and at the same time it also depends upon the distance of point P from the source charge. Now you should understand that electric potential as well as the electrostatic potential energy both are scalar quantities. They are just simply the counterpart. If you see in the first chapter we discussed about electric forces and electric field. Electric forces was defined for pair of charges and electric field was defined due to a source charge. But both those quantities were vector in nature. Here you are finding at electrostatic potential energy and electric potential. Electrostatic potential energy is defined for a pair of charges and electric potential is defined due to a source charge. But here both these quantities happens to be a scalar quantities, friends. So these are some important aspects of this was the derivation for electrostatic potential energy between pair and electric potential due to a source charge. I have obtained the expression for them. Please take care about it. Now I am going to discuss the important properties associated with them. Now properties associated with electrostatic potential and potential energy. Remember friends, potential energy is a scalar quantity, hence they will be following the law of algebraic addition. That's the important thing that you should keep in your mind. It's a scalar quantity, so it will be just added like pure numbers. Now potential energy due to like charges are always written with a positive sign, whereas potential energy due to unlike charges are written with a negative. So if I have got a pair of like charges, let's say this is a plus Q and this is again a plus Q2. So this is Q1 charge, this is Q2 charge. They are separated by some distance R1 apart. So what will be the potential energy of this pair of charges? Potential energy for this pair of charges will be 1 upon 4 pi epsilon naught Q1 Q2 upon distance between them R1. Now this is the potential energy which is going to be written with a positive sign. Like pair, so it will be always mentioned with a positive sign. Suppose similarly this is a negative charge Q1, there is another negative charge Q2. Now once again you should understand, and the distance between them let's say as A. So what will be the potential energy of like pairs? So these are the like pairs of charges. So remember, like pair will have this positive potential energy. So plus 1 upon 4 pi epsilon naught. Once again, what is the potential energy in this case? Q1, Q2, and what is the distance between the separation? That is A. So that is how you are going to write down the potential energy due to like pairs. So like charges. Similarly, instead of a like, if I have got one positive charge Q1, another charge negative in nature, and let's say Q2, and the distance between them let's say happens to be X, and I ask you now what will be the potential energy of the system? There is minus. Why minus? Because it is an unlike pair. So you write down with a sign. Potential energy comes with a sign. Minus 1 upon 4 pi epsilon naught Q1 Q2 by X. Now these are the expressions for potential energy. Now you need to understand the expression of potential energy that you have studied is 1 upon 4 pi epsilon naught Q naught upon distance of separation. This Q and Q naught happens to be the magnitude of charges, and when I am saying they are magnitude, I am not going to include the nature of the charge. That means I am not going to include positive or negative charges. Plus sign or minus sign we are not going to include. X being the distance of separation between the two. Distance of separation. So please understand, here they are the magnitude of the charges. Here this is the distance of separation. The sign that you are putting it up, whether plus or minus, in this expression comes from the fact whether the charges are like or whether the charges are unlike. Majority of you as a student, I have seen that you try to take up the sign with these with the Q1 and Q2. Q1 and Q2 in the expression, they do not carry the sign. They are there to suggest to you only the magnitude part. Please take care about this important aspect of the expression. The third important property is, as I told you, potential energy between a pair of charges is written as 1 upon 4 pi epsilon naught, may be positive, may be negative, okay, that depends upon the nature of the two charges, q1 q2 by distance of separation. So it depends upon the magnitude. Remember friends, again and again I am saying it depends upon the magnitude, q1 q2, magnitude of charges, and then distance of separation between them. Please take care. Number of time I have seen the students committing the mistakes. So it depends upon magnitude, it does not depend upon the nature, and then it depends upon the distance of separation. Now potential energy does not depend upon the manner in which you have assembled the charges or the way you have brought them to those 2 points. It only and only depends upon the initial and final position. So potential energy depends upon the initial and final position of the charges. It is independent of the manner in which you are assembling the charges. If the potential energy anywhere comes out to be negative, then you call such pair of charges as bound charges, and then you need to give some energy to break or separate the charges, and the amount of energy needed to separate the two charges are going to be referred as binding energy of the system. So suppose in an atom, I believe you are all aware of, the atom consists of a nucleus, let's say a hydrogen atom. So in a hydrogen atom, what you would find, in the nucleus you will have one proton, and the electron revolves around this proton. Electron being a negatively charged particle, proton being a positively charged particle, they are certain distance apart. Let's say the distance of separation between them is r. So what will be the potential energy of the system? The first thing that you should remember, it is a negative, because one is positive and another one is negative, so the potential energy will be negative 1 upon 4 pi epsilon naught. What is the charge possessed by a proton? That is elementary unit of charge E. What is the electron, the magnitude of the charge possessed by an electron? That is also elementary unit of charge E. So it will be q1, that is E, q2, that is E, and the distance of separation will be r. So this comes out to be minus 1 upon 4 pi epsilon naught E square upon r. So this potential energy is called as binding. This potential energy comes out to be negative. So the system or the pair of charges is bound. Now the binding energy is the energy needed to separate them. So you need to provide this much amount of energy. The binding energy will be positive 1 upon 4 pi epsilon naught E square by r, and that becomes my binding energy of the charges, friends. Now if the charges are separated at infinite distance apart, then the potential energy of them is considered as 0. So that becomes my reference. I have taken, if you remember in defining also, we have taken infinity as the reference point from where you have brought. So that reference point, the infinity will be treated as our reference point, and the potential energy at the reference point is considered as 0, friends. So that is what you should take care about. If there are more than 2 point charges in the system, the total potential energy will be obtained by finding the sum of all the potential energy. And what type of sum? Remember, potential energy is a scalar quantity. So you are going to go for algebraic sum of all the potential energy of the pairs which have formed the system, and then it will give me the potential energy of the system, or I can also say that will give me the amount of work done in assembling the two charges together, friends. Let's say I have got 3 charges in a system. This is q1, this is q2, and this happens to be Q3. The distance between Q1 and Q2 is, let's say, A. The distance between Q2 and Q3 happens to be B, and the distance between Q1 and Q3 happens to be C. Q1 is a positive charge, Q2 is also a positive charge, and Q3 is also a positive charge. So if I am looking for the potential energy of the system, so what will be the potential energy of the system? How I am going to find out the potential energy of the system? Potential energy of the system is going to be the potential energy, sum of all the potential energy between the pair of charges. So how many pairs I have got? Let's start with, this is my one pair, let me label it as 1. This is my second pair, let me label it as 2. And this becomes my third pair, let me label it as 3. So let's go ahead with the potential energy of the pair of the charges. Now this potential energy between the first pair, how are the nature of the charges? They both are like nature, so potential energy will be positive. And the magnitude of this potential energy will be 1 upon 4 pi epsilon naught Q1 Q2 upon the distance of separation, that is A. Similarly, let's go ahead and find out the potential energy of the second pair. The potential energy of the second pair will be plus Y plus, again they are like pairs, and 1 upon 4 pi epsilon naught Q2 Q3 upon B. And then you can also go for the third pair. Now going for the third pair, this is also a like pair, so potential energy will be again positive, 1 upon 4 pi epsilon naught Q1 Q3 by C. Now potential energy all will be expressed in joule, and potential energy is a scalar quantity, so the net potential energy of the system, will simply be the algebraic sum of potential energy between each pair. So potential energy 1, potential energy 2, potential energy 3. So putting it over here, so 1 upon 4 pi epsilon naught Q1 Q2 by A plus 1 upon 4 pi epsilon naught Q2 Q3 by B plus 1 upon 4 pi epsilon naught Q1 Q3 by C. Taking 1 upon 4 pi epsilon naught common, you get Q1 Q2 by A plus Q2 Q3 by B plus Q1 Q3 by C. So that becomes the potential energy for the pair of system of charges. Now if I ask you, the same question can be brought to you in another pattern also. Suppose if I say all the three charges were placed at infinite distance apart, and then you are bringing it on the vertices of a triangle whose sides are as A, B and C, then find out the work done in assembling the charges. Now friends, when these three charges were at an infinite distance apart, the potential energy initial was 0. And when you have assembled it in this form, then the potential energy final is what you have just now calculated. So work done in assembling will be equal to difference of potential energy or change in potential energy. That is, change always means final minus initial, and that comes out to be 1 upon 4 pi epsilon naught Q1 Q2 by A plus Q2 Q3 by B plus Q1 Q3 by C. So with the help of potential energy, you can also find out the work done in assembling the system of charges, friends. This particular concept is very, very important for your board examination, and you should understand that this type of question will always can be asked in your examination also. Now as another example, let me take charges to be placed at the vertices of a square. So this is positive Q1, this is minus Q2, this is plus Q3, and this happens to be minus Q4. All the 4 charges are placed at the vertices of a square. We are required to find out the potential energy of the system, friends. So there are 4 charges. So how many pairs? Now counting the number of pairs is going to be the most typical work in this particular example. Now how many pairs? This is my 1 pair, isn't it? This becomes my second pair. This becomes my third pair, friends, while this becomes my fourth pair, isn't it? Now there are 2 more pairs. Can you see over here? This becomes my diagonal pair. There is 5th pair, and this becomes my 6th pair. So how many pairs of charges are here? There are 6 pairs of charges. Now what you need to do, you need to find out the potential energy due to each pair of charges. And I give you a tip over here. In order to find out the number of pairs, always cross check it with the formula NC2. What is N over here? The number of charges present. So how many number of charges are there? 4 C2. In your calculator, if you go for this calculation of 4 C2, you will always land up with an answer of 6. So there are 6 pair of charges. So this is a trick to find out the pair of charges. So NC2 will defines the pair of charges for me. I have already mentioned it over here. Now let's find out the potential energy between each pair. So the first pair will have a potential energy. Now first look what nature. Like or unlike? They are unlike nature. So unlike nature, I put a minus sign. What will the potential energy of this pair? 1 upon 4 pi epsilon naught Q1 Q4 upon the distance of separation. It's a square, so let's call the edge as A. So upon A. This much joule. Similarly for the second pair, like or unlike, this is also unlike pair, so negative sign. 1 upon 4 pi epsilon naught Q1 Q2, the distance of separation between A, because it's a square of edge A, so A joule. Now what is the third pair? Potential energy of the third pair, that was Q2 and Q3. Are they like or unlike? They are unlike, so again minus. 1 upon 4 pi epsilon naught Q2 Q3. What is the distance of separation once again? Being a side of a square, all sides are equal, so again A joule. Now what is the fourth pair? That is Q4 and Q3. Like or unlike? It is unlike, so minus Q4 Q3 by A joule. Now the fifth pair. What is the fifth pair? They are the diagonal pairs. Now the fifth pair was labeled between Q4 and Q2. How are they, friends? Q4 and Q2, they are like or unlike? They are like charges. Both are negatives. So this potential energy will be written with a plus sign. And this will be 1 upon 4 pi epsilon naught Q4 Q2 upon the distance of separation. That distance of separation is the diagonal of the square. And that happens to be A root 2 joules. I believe you all know how to calculate the diagonal. So I've just written down directly. Now, is there any pair left? That is the sixth pair. What is the potential energy of the sixth pair? What type of charges are we having? Once again, we are having a like pair of charges. So this will be plus, like, so plus Q1 and Q3. So 1 upon 4 pi epsilon naught Q1 and Q3. And what is the length of the diagonal? Once again, our distance of separation, A root 2 joules. So this happens to be the potential energy due to each pair. That's what first thing you have to do. And then what I need to find? I need to find the potential energy of the system, friends. Now potential energy of the system is going to be the algebraic sum of potential energy due to each charges. Isn't it? So let's do the sum. So add them. You will find that 1 upon 4 pi epsilon naught is common and 1 upon A is also common. I have taken them common, and then I have got minus Q1 Q4 by A minus q1 q2 by a minus q2 q3, sorry, a has already been taken out, sorry friends, so this a is not there, has already been taken, minus q2 q3, then minus q4 q3, and then I've got plus q4 q2 upon a root 2 and plus q1 q3 by a root 2, and this will give me the total potential energy, friends. So friends, try out these problems. This can be the most difficult one from the concept or from the board point of view. You can try out charges placed at the vertex of a hexagon or pentagon if you want to go for more complex problems. Else this is the most complex problem that you can have from the console. So these were certain properties associated with electric potential energy, friends. Now let's review the properties of electric potential, friends. Now the very first property of electric potential is that electric potential is also a scalar quantity, and hence it's going to follow the law of algebraic addition. Secondly, electric potential due to a positive charge is always going to be written with a positive sign, and electric potential due to a negative charge will always be written with a negative sign. So suppose here you have got a positive Q charge, and I am interested in stating the potential at point P, which happens to be situated at certain distance r from this source charge. So this becomes my source charge. So the potential at point P due to the source charge Q will be plus. Why plus? Because potential due to a positive charge is considered as positive. 1 upon 4 pi epsilon naught Q by R. Suppose the source charge would have been negative. Now if my source charge is negative and I am looking for some potential at point P2, which happens to be situated at some distance r apart, then this potential Vp2 will be minus 1 upon 4 pi epsilon naught Q upon R. Remember, so friends, potential depends upon two factors: magnitude of the source charge and the distance between the source charge and the point where you are interested in finding out the electric potential. SI unit of potential was volt, so you can always terminate this in terms of volt. Okay friends, so units are must. So electric potential, as just now I told you, depends only upon two things: the magnitude of the source charge and the distance between the point and the source charge. Now if the charge is if the point is situated at infinite distance apart from the source charge, then the electric potential at infinity is always considered as 0, and that will be considered as my reference point, friends. Now electric potential always decreases along the direction of electric field. Suppose this is the direction of electric field, or this arrow represents any electric field lines, friends. Then as you move along the electric field line, the electric potential will always be decreasing. So at point A and point B, as you move from A to B, the potential will always be decreasing. So remember friend, potential of A will always be greater than the potential of B. Now this you should remember. Potential always decreases as you go or as you move along the direction of electric field. Now the second thing that you should remember, if I place a test charge, if I place a free positive charge, then this free positive charge would always move from the point of higher potential to a point of lower potential. So if I am placing a positive charge, a free positive charge, so this free positive charge would tend to move from a region of higher potential to a region of lower potential. To the contrary, if I place a negative charge, then the negative charge would tend to move from a region of lower potential to a region of higher potential, friends. Take care about this fact. So a positive charge always moves from a region of higher potential to a region of lower potential, and a negative charge would always move from a region of lower potential to a region of higher potential, and potential always decreases in the direction of electric field. So that's three very important aspects, friends. Now, how do we define 1 volt? SI unit of electric potential, as I told you, is 1 volt. And how do we define as 1 volt? 1 volt is defined as the potential at a point when 1 joule of work is done by the agent in bringing 1 coulomb of charge from infinity to that point with infinitesimally slow constant speed. I hope this point is clear to all of you. Friends, let's draw the graph for electric field and electric potential with variation with distance due to any point charge. Remember, friends, electric field used to vary inversely proportional to the square of the distance, whereas electric potential varies inversely proportional to r. So on the y-axis I am plotting electric field or potential, both are being plotted on the y-axis, whereas in the x-axis represents the distance from the point charge. So the point charge is supposed to be placed at origin. So point charge is placed at the origin. This is my origin, and as I move away from the point charge, electric field is going to vary rapidly proportional to 1 by r square. So friends, this electric field is varying proportional to 1 by r square hyperbolically. And whereas if I plot a potential, then potential varies inversely proportional to r, so it is a rectangular hyperbolic graph. So V is proportional to 1 by r. Remember, friends, this graph is not up to the scale, and also you should understand that at a unit distance from the point charge, both electric field and potential will be equal in magnitude. So at this unit distance from the point charge, both electric field and potential will be equal to each other, friends. And as I told you, this graph is not drawn up to this scale. So this graph is also pretty important for you to understand, so please take care about this particular graph. Now friends, I leave you with two questions. You have to determine the net electric potential at this point P due to two charges, one being negative charge, another being positive charge, and this is located, these charges are situated at a distance of 2L from each other. M happens to be the midpoint and the distance of M to point P happens to be R. So this is a combo of two charges, one negative, another positive. Similarly over here you can take another one, again a combo of these two charges, negative and positive. M being the midpoint, this M is midpoint, this distance is R, friends, and this distance happens to be 2L. So what you need to do, you have to find out the potential at point P. Please solve these two problems. This will eventually lead us to the derivation for the result of electric potential due to a dipole. So these two questions are very, very important. Do them and then we will discuss them later in the next video. Friends, thank you for watching. Don't forget to give a like और comment. अगर अभी तक आपने मेरे इस चैनल को सब्सक्राइब नहीं किया है तो please do the same. Don't forget to hit the bell icon so that whenever a new video is loaded, you get the notification. Take care and we will meet back again with a new video and a new solution. Thank you, friends.